We are going deep, like subatomic deep. We're talking quarks.
Oh, yeah. Quarks.
You know, you've heard of atoms, right?
Of course.
But have you ever wondered what makes up those teeny tiny building blocks?
Well, that's where quarks come in?
Exactly. Quarks are even tinier particles, and get this, they make up the protons and neutrons that are at the heart of every atom.
They're the fundamental building blocks of matter, you could say.
And we've got a whole stack of research here ready to break it all down.
It's like peeling back the layers of an onion, starting with the basics and then...
Getting to some pretty mind-bending stuff.
Yeah, quarks can get pretty weird.
Okay, so for our listeners who are just getting their feet wet with particle physics, let's start with Quarks 101. What are these things, really?
All right, so first thing to know, quarks are never found alone, ever.
Really? They're like the ultimate clingers.
They always exist in groups, bound together by this incredibly strong force.
Strong enough to keep them from ever going solo, huh?
Exactly. And that force is aptly named the strong force.
So tell me more about this permanent huddle they're in.
Well, there are 6 types of quarks, and they have some pretty interesting names. Up, down, charm, strange, top and bottom.
6 types, huh? It's like choosing flavors at an ice cream shop.
Ha! That's a good analogy. And just like how different ice cream flavors create unique combinations, different quarks combine to create all the different particles we find in the universe.
Okay, so give me an example of a quark combo that creates something we all know and love.
All right, so imagine 2 up quarks and a down quark. Put those together, and you've got a proton with its positive charge.
Okay, that makes sense. Protons, the positively charged particles in an atom's nucleus. Got it.
Now, switch that up a bit. 2 down quarks and an up quark, and boom, you've got a neutron with no charge.
So quarks are like the ingredients, and protons and neutrons are the finished dishes, right?
You got it.
But here's where things start to get a little, shall we say, quirky. Our research mentions something called color charge. Are we talking like the rainbow here? ROYGBV.
Not exactly. It's not about the colors we see. Think of it like a force, similar to magnetism, but instead of attracting and repelling, it binds quarks together.
Oh, okay, so it's more like a code or a label that determines how they stick together.
Yeah, you could say that. It dictates how they interact with each other.
All right, color charge. I think I'm starting to get it. But there's something else that's throwing me off, this whole idea of fractional charges.
Yes. That's where quarks really start to challenge our everyday understanding of physics.
Our sources say quarks have a fraction of an electron's charge. How's that even possible? Can you have, like, half a charge?
It's pretty wild, right? It's one of the things that makes quarks so unique.
So how does that work?
Well, you see, this fractional charge, when combined with that color charge we were just talking about, determines the charge of the larger particles they form, like those protons and neutrons.
So it's all connected. The type of quark, its color charge, and its fractional charge all play a part in the final product.
Exactly. It's a beautifully intricate system.
Okay, I'm starting to see how this all fits together. But tell me more about this strong force that's keeping all those quarks in their permanent huddles.
Right, so remember how I said quarks get weird?
I have a feeling you're about to tell me just how weird.
Well, it turns out that the strong force, the one that binds quarks together, actually gets weaker the closer they get to each other.
Huh. Wait, so it's like they have a fear of intimacy? I thought the closer you are, the stronger the attraction.
It's totally counterintuitive, right? It's a phenomenon called asymptotic freedom, and it really challenges our typical understanding of how forces work.
Asymptotic freedom, that's a mouthful. But it's like they're rebels, defying the laws of attraction as we know them.
In a way, yeah. And it suggests that at incredibly high energies, like those found in the very early universe, quarks might have behaved very differently than they do today.
Okay, now my mind is really blown. But here's another question that's been bugging me. If we can't even see these quarks individually, how do scientists even know they exist? It seems like trying to study ghosts.
It's a great question, and it requires some pretty incredible tools. Scientists use massive machines called particle accelerators to smash particles together at unbelievably high speeds.
So it's like a demolition derby on a subatomic scale?
Exactly. These collisions create a shower of new particles, and by analyzing the debris, they can infer the properties of the quarks that were involved.
So like trying to figure out what a cake is made of by smashing it against a wall and studying the crumbs?
It's a messy but effective method for probing the universe's fundamental building blocks. And through these experiments, they've developed a whole intricate theory to explain how quarks interact.
A theory. Tell me more about that.
It's called quantum chromodynamics, or QCD for short.
QCD. Got it. So that's like the rule book for how these particles behave.
Exactly. And while QCD has been incredibly successful in explaining a lot of what we see, there are still some big mysteries surrounding quarks. Like, why are they always confined? Why can't we ever find a single quark just hanging out by itself?
Yeah, that's what I was wondering earlier. It's like they're allergic to being alone.
It's one of the biggest unanswered questions in particle physics.
Well, we've covered the basics. Quark flavors, color charge, fractional charges, and how scientists study these invisible particles. But our sources dive into even more fascinating territory, like something called Quark-Gluon plasma.
Ah, yes, Quark-Gluon plasma. Now things are really going to get interesting.
All right, bring on the weirdness.
Just imagine a state of matter so hot and dense that quarks are no longer confined within those familiar protons and neutrons. Instead, they're free to roam around in a sort of chaotic soup.
Quark soup. Okay, now I'm really intrigued. Where would we even find something like that?
Well, scientists believe that quark-gluon plasma existed in the very first moments after the Big Bang.
Wow, so we're talking about the primordial soup of the universe here.
Exactly. And get this, they've even managed to recreate tiny droplets of it in particle accelerators.
So we're recreating the conditions of the early universe right here on Earth.
It's pretty amazing, isn't it?
So what can studying this quark soup tell us?
It can help us learn a lot about the fundamental forces that shaped our universe, and potentially uncover some of the mysteries surrounding the earliest moments of existence. But, you might think we've got quarks all figured out with those 6 flavors and unique charges we talked about.
You're about to tell me there's more, aren't you?
Oh, there's always more. There are these rule-breaking particles out there called exotic hadrons that kind of throw a wrench in things.
Wait, particles that don't follow the usual quark combination rules, like rebels of the subatomic world?
You could say that. Some of these exotic hadrons have 4 quarks instead of the usual 3.
4 quarks.
We call them tetraquarks. And some even have 5 quarks called pentaquarks.
Okay, now we're really going off a beaten path. 5 quarks in one particle. What do these exotic hadrons tell us about the strong force?
That's what scientists are trying to figure out. They're like puzzles, challenging us to understand how they're bound together and what their existence means for our understanding of the universe. And if that wasn't enough, we've also got this thing called the proton spin puzzle.
A puzzle about spin. What's so puzzling about that?
Well, you see, we know that protons have spin, but when we add up the spins of their constituent quarks, the numbers just don't add up.
So there's more to the story of how those tiny particles get their spin, like there's some missing piece of the puzzle.
Exactly. And that's just the tip of the iceberg.
All right, listeners, buckle up, because we're about to dive even deeper into the world of quarks.
Welcome back. We've been exploring the wild world of quarks, those tiny particles that make up everything we see and touch.
Yeah, we've talked about their flavors, their color charge, this weird asymptotic freedom thing.
Right, and how scientists study them by smashing particles together at incredible speeds.
It's like a subatomic demolition derby. But our sources go even deeper, talking about some pretty complex theoretical frameworks.
Yeah, like effective field theory. It sounds kind of intimidating, but it's actually a way to simplify things.
Simplify things. How do you simplify the world of quarks?
By focusing on specific interactions that are relevant at a given energy scale.
Okay, so it's like using a different lens to look at the same object.
Exactly. Like, imagine you're trying to understand how a car engine works. You don't need to know about every single nut and bolt, right?
I guess not.
You can focus on the major components and how they interact. Effective field theory is kind of like that. It helps us zoom in on the most important aspects of quark interactions.
Got it. So what are some examples of these lenses that physicists use?
Well, one is called chiral perturbation theory, or GHPT.
GHPT. Okay, I'm taking notes.
It's especially useful for studying the interactions of pions and other light mesons, which are particles you might have heard of at low energies.
So it's like a specialized tool for understanding how these lighter particles behave.
Exactly. And then for when we're dealing with heavier quarks, we have heavy quark effective theory, or HQET.
HQET. All right, another acronym to add to the list. What's that one all about?
This theory is really helpful when studying hadrons that contain heavy quarks, like those charming B mesons. And B mesons, they're key to understanding some really big mysteries.
Like what?
Like CP violation, have you heard of that?
I think so, but remind me.
It's a phenomenon that helps explain why there's more matter than antimatter in the universe.
Okay, no, that's a big deal.
Yeah.
So HQET helps us understand not just quarks, but also why we exist at all.
In a way, yeah. It's pretty amazing how all of this connects.
It really is. Our sources also mention something called anomalous magnetic moments. It sounds a bit like a superhero origin story to me.
Huh, I can see that. Basically, quarks have these magnetic properties that are a bit more, well, anomalous than we'd expect based on their spin and charge.
Anomalous, huh? So they're even more magnetic than they should be.
Yeah, it's like they have this extra magnetic oomph.
But what does that tell us about the universe? Why is that significant?
Well, these anomalous magnetic moments come from these tiny quantum fluctuations, and they're a clue that there might be more to the story than our current models predict.
More to the story. You mean like new particles or forces that we haven't discovered yet?
Exactly. It's like those anomalous moments are whispering secrets about the universe that we're just starting to decipher.
Okay, now I'm really hooked.
Yeah.
So how do scientists actually study these anomalous magnetic moments?
Well, one way is through a process called deep inelastic scattering.
Deep inelastic scattering. That sounds intense.
It is. Scientists use particle accelerators to fire these high-energy particles, like electrons or neutrinos, at protons or neutrons.
They're like shooting tiny bullets at quarks.
Kind of, yeah. And by studying how those particles scatter off the quarks inside, they can start to piece together a picture of what's happening inside the hadron.
So it's like a high-stakes game of billiards, but on a subatomic scale.
Exactly. And from these scattering experiments, they've developed a model to describe hadrons.
A model. What's that called?
It's called the parton model. It describes hadrons as being made up of these point-like particles called partons.
Partons, okay. What exactly are partons?
They can be quarks, antiquarks, or even gluons.
Right, gluons, those are the particles that carry the strong force, right?
Exactly. And the way these partons are distributed within a hadron tells us a lot about how the strong force works at different energy levels.
This is getting pretty complex. Our sources even go on to talk about things like the renormalization group. I'm not even sure where to begin with that one.
The renormalization group is a pretty powerful concept. It helps us understand how the strength of the strong force changes depending on the energy at which we're looking at it.
Okay, so how does that work? Does the strong force get stronger or weaker at higher energies?
Well, that's where things get really interesting. At very high energies, like those found in the early universe, the strong force actually gets weaker. Remember that asymptotic freedom we talked about?
Right, the quark's aversion to intimacy.
Exactly. But at lower energies, the strong force gets much stronger, and that's what leads to that confinement of quarks within hadrons.
So it's like quarks have a split personality. They act differently depending on the energy of their surroundings.
You could say that. And this change in the strength of the strong force is described by something called the beta function.
Beta function, got it. So are we basically saying that the strong force is this constantly shifting dynamic force?
Exactly. It's a fascinating and complex force, and there's still a lot we're learning about it.
Our sources dive even deeper into some really complex stuff like non-perturbative QCD and lattice simulations. Are we going to need a supercomputer just to understand quarks?
Well, some aspects of QCD are so complex that they can't be solved using the usual mathematical tools. That's where non-perturbative methods like lattice QCD come in.
Okay, break that down for me. What in the world is lattice QCD?
Imagine taking the fabric of space-time and representing it as a giant 3D grid.
A grid, like a chessboard.
Yeah, kind of. On this grid, we can simulate the interactions of quarks and gluons using powerful computers.
So it's like creating a virtual universe inside a computer.
Exactly. And in this virtual universe, we can study the strong force in all its messy glory.
That's incredible. So they're like playing SimQuark on a supercomputer. What have they learned from these simulations?
Lattice QCD has helped us understand a lot about things like quark confinement, the masses of hadrons, and even the properties of those exotic particles we talked about.
Right, those tetraquarks and pentaquarks. It's still mind-blowing to me that particles like that even exist.
They really challenge our understanding of how quarks interact.
Exactly. If we can't even see individual quarks, how do we know that those exotic combinations are really out there? It's like we're trying to solve a puzzle, but some of the pieces are invisible.
It's a great analogy, and that's where things get even more interesting. Scientists have to get pretty creative to study these exotic hadrons.
So how do they do it?
Well, they look for telltale signs in the debris of particle collisions.
So back to the demolition derby.
Exactly. When they smash particles together at high energy, sometimes they see these unusual patterns in the particles that fly out.
Patterns that suggest the presence of these exotic particles.
Exactly. It's kind of like looking for footprints in the sand. You might not see the creature that made them, but you can infer its existence from the tracks it left behind.
So by analyzing the debris from these collisions, they can say, aha, it looks like a tetraquark was here.
Exactly. And it's not just about the types of particles they find, it's also about their energy and momentum, how they're moving and interacting. By carefully analyzing all of this data, scientists can piece together evidence for the existence of these exotic hadrons.
It's like they're playing cosmic detective, using the clues from these collisions to uncover the secrets of the subatomic world.
I like that. And speaking of secrets, our sources mention some even more mind-bending concepts like quantum entanglement and this thing called the AD-SCFT correspondence.
Yeah, these are some seriously heavy topics. I've heard about quantum entanglement, this idea that particles can be linked together in a way that defies our everyday intuition.
Exactly. It's this bizarre phenomenon where two particles, even if they're separated by vast distances, can be connected in such a way that their fates are intertwined.
So it's like they have this telepathic connection, even across galaxies. I remember Einstein called it spooky action at a distance.
He did. And while it might seem like something out of science fiction, entanglement is a very real phenomenon that has been experimentally verified.
Okay, so entanglement is real, but how does it relate to quarks specifically?
Well, think about the quarks inside a proton or a neutron. They're constantly interacting with each other through the strong force, exchanging information and energy, and these interactions can lead to a high degree of entanglement between the quarks.
So the quarks inside a single proton are like a tiny entangled network. Their destinies intertwined.
You got it. And this entanglement isn't just a theoretical curiosity. It has real implications for how we understand the structure and behavior of hadrons.
Okay, I'm starting to see how these seemingly abstract concepts connect to the tangible world of particles. But what about this AD-SCFT correspondence? That one sounds even more intimidating.
It's a truly mind-bending concept, but bear with me because it's worth exploring. Essentially, it suggests a deep connection between gravity and quantum field theory.
Okay, so we're talking about linking the physics of black holes to the physics of quarks.
Exactly. It might sound crazy, but this correspondence, sometimes called the Maldacena duality, has led to remarkable insights in both areas of physics.
But how can two such different realms of physics be connected?
That's the beauty of it. The AD-SCFT correspondence says that a theory of gravity in a higher dimensional space called anti-de Sitter space, or ADS, is mathematically equivalent to a certain type of quantum field theory called conformal field theory, or CFT, in a lower dimensional space.
So we're talking about different dimensions here, like something out of a science fiction movie.
It does sound a bit like that, but the mathematics behind it is solid. And what's really exciting is that the theory on the CFT side of this correspondence can be used to describe strongly interacting systems, like those governed by QCD.
So by studying gravity in this higher dimensional 8A space, we can gain insights into the behavior of quarks and gluons.
Exactly. It's like using a different language to describe the same physical phenomena. And this approach has led to some remarkable progress in understanding quark confinement, the spectrum of hadrons, and even the properties of Quark-Gluon plasma.
It's like looking through a cosmic lens to see the world of quarks reflected in the dance of gravity. But with all of this incredible progress, where do we go from here? What's next in the world of quark exploration?
The future is incredibly exciting. We have new generations of particle accelerators being built, like the high-luminosity Large Hadron Collider, which will allow us to smash particles together with even higher energies and precision, creating more opportunities to study those elusive quarks.
It's like they're building a more powerful microscope to peer even deeper into the subatomic world.
Exactly. And we also have proposed projects like the Electron-Ion Collider, which would give us a much clearer picture of the Quark-Gluon structure of matter.
So we're talking about even more powerful tools to unlock the secrets of the subatomic world. But even with all these advancements, I imagine there are still so many fundamental questions about quarks that keep physicists up at night.
Absolutely. We still don't fully understand the origin of quark masses or the intricate details of confinement. And then there's the strong CP problem, this puzzle related to the imbalance of matter and antimatter in the universe.
So even with all we've learned, there's still so much more to discover.
Always. And that's what makes this field so captivating. The pursuit of knowledge, the exploration of the unknown, that's what drives us forward.
Well, listeners, we've certainly covered a lot of ground in this deep dive. We've journeyed from the basics of quark flavors and colors to the frontiers of quantum entanglement and the AD-SCFT correspondence. We've learned how scientists study these elusive particles, uncovered some of the mysteries they hold, and glimpsed the exciting future of quark exploration. But remember, This is just the beginning of your own journey into the fascinating world of particle physics.
There's a whole universe of knowledge waiting to be discovered and countless questions still unanswered. So keep that curiosity burning and never stop exploring the fundamental building blocks of our amazing universe.
Thanks for joining us on this incredible adventure into the world of quarks. Until next time.